Hello everyone. Today I will be presenting our paper CLR Channel-Wise Lightweight Reprogramming for Continual Learning. First, I will provide some background. The primary focus of our paper is to address the issue of catastrophe forgetting of continual learning. One of the key distinctions between continual learning and multitask learning is data accessibility. In multitask learning, all data sets are accessible simultaneously, whereas in continual learning, only one dataset is available at a time, and previous datasets become inaccessible. There are three primary approaches to continual learning: regularization methods, dynamic network methods, and replay methods. Our paper aligns with the dynamic network methods category. When learning new tasks, our method introduces a new set of parameters specific to that task. A key advantage of our approach is its efficiency in terms of memory and computational costs. Our paper is titled Channel-Wise Lightweight Reprogramming. The term reprogramming signifies that we employ a fixed backbone architecture for all tasks, which can be reprogrammed to adapt to each specific task individually. Our work draws inspirations from several previous studies. The first is the paper Adversarial Reprogramming of Neural Networks, which successfully demonstrated that reprogramming the input space can enable a network to solve an entirely different task. The second is lightweight lifelong learner, which shows that even a small number of parameters can significantly shift the model's representation space. Lastly, GhostNet reveals that the feature maps of a single convolutional layer can be highly similar following a linear transformation. In our architecture, each convolutional block is augmented with a CLR layer immediately following the standard convolutional layer. The gray portion of architecture remains identical to the pre-trained model as is kept fixed throughout the learning process. For each channel in the feature map generated by the convolution layer, we apply a 3x3 channel-wise convolution, as opposed to a traditional convolution layer. This results in significant parameter savings. To further optimize the parameter count, we omit the CLR layer following any one-by-one convolution layers. Consequently, the total additional parameter introduced by our method amount to just about 0.6% of the overall network size. Thus, for each task, we have specific reprogramming parameters and a linear head during the learning phase. During testing, a task oracle is required to extract these specific parameters for the corresponding task and performs clarification. We utilize a new dataset known as Scale 102, which is introduced in the paper Lightweight Learning for Shared Knowledge Lifelong Learning. To visualize the characteristic of this dataset, each circle represents a task. The size of the circle indicates the number of images in that task, while the color signifies its objective. For instance, some tasks are geared towards scene understanding, whereas others focus on object counting. The border of the circle reflects the nature of the images. Some may be artificial, like animation, while others are real-life images. This dataset offers a more comprehensive representation of real-world tasks compared to previous datasets. For our study, we use a subset of Scale 102 that contains 53 tasks rather than the full set of 102 tasks. We can examine the detailed statistics of our dataset in comparison to previous datasets. As for the main results of our method on the dataset, we employ a ResNet-50 model portraying on ImageNet as the backbone for all methods. It shows that average accuracy of tasks learned so far. As evident from the results, our method outperforms all previous baselines. Here, we present the performance matrix for the initial two tasks. The key takeaway is that our method exhibits no decline in performance across these tasks. Additionally, we provide the final performance matrix for all 53 tasks after the learning process is complete. We also present a comparison of the memory and computational costs of our method relative to existing baseline. Our method's memory cost is approximately only 0.6%, significantly lower than other methods that achieve comparable performance, like subsub and ER. Additionally, we demonstrate that our math model can achieve high performance even without relying on a pre-trained ImageNet backbone. Finally, we demonstrate that our method is also applicable to transfer learning. Thank you.